Okay, so reviewing from last day, we have our displacement time graphs, often called position time graphs. If it's linear, what kind of motion is it? Constant motion, so uniform motion. So we are allowed to use this formula here. D equals VT, okay? And if you think about this formula, D equals VT, which is the dependent variable and which is the independent variable? What's changing and what responds? Yeah, the displacement depends on the time, depends on how long you're traveling at your speed or velocity. So this is like your y variable and this is your mx. You might remember that from mx plus b. You remember that for a linear relation? So what we come to realize is that the slope of a distance time graph is just your speed. And that is an absolute must. You need to know that, okay? Now, your average velocity formula that you've been using, which is, you know, the average velocity change in position over time, and you could make a note of this in your notes, this formula can only be used for uniform motion. As soon as you start to have a curved graph, you can no longer use this. As soon as there's acceleration, this is no longer valid for the entire trip. Okay? It's valid in a moment of time, but not for the entire trip if there's acceleration going on. Okay? If there's acceleration going on, your displacement time graphs will look like these, and these are quadratic. And if you're in Math 20-1, you'll learn more about these. If you've already taken Math 20-1, you know what this is. But these are just polynomials of degree 2. Okay? So there's an extra term. So there's actually 3 terms. So it looks like kind of like this. ax squared plus bx plus c. And when we get to, this is for non-uniform motion. And then when you guys get your formula sheets and we get into the kinematics equations, you'll actually see a second degree polynomial formula that involves acceleration. And it kind of looks like this. Displacement depends on your initial velocity times t plus 1/2 the acceleration times time squared. And we'll get into this in a few days here, hopefully by Wednesday. Okay, so this is for the non-uniform motion. This is when you're accelerating. And we're going to talk a little bit about that today. Okay, so you can just quickly jot this down. So you have your linear relationship, which is uniform. You have your quadratic relationship, which is non-uniform. One has no acceleration, and this one has acceleration. And you have a linear graph versus a curved graph. Okay, so that was the quiz. And now we're going to start a fresh sheet. Okay, so this is just still 2.1 continued. There's a big section. There's like 30 questions. There was questions for uniform velocity. There was graphing questions. There was DT graphs, and there was VT graphs. If you guys remember, that's where we threw on the brakes, remember? We said stop. We didn't have any notes for VT graphs, okay? So let's consider a car moving with constant velocity to the right. So constant rightward velocity. So it's positive. So with one dimensional, one direction's got to be positive, the other's got to be negative. So east versus west, a north versus south, whatever direction you're going, just pick one of them to be positive, and that will be east or north, depending on which direction you're going. Okay, and we will say it's 10 meters per second. Okay, so this tells us that we have 0 acceleration. because it's moving at a constant velocity. So there's no acceleration. Okay, so if you guys want to come grab some rulers, or you just use your ID card or something, but we'll just be sketching a few graphs today, so it's better if they're straight. So while you're getting your straight edges, I've just drawn there a VT graph. So now we're not doing position time, we're doing velocity versus time. So if you have a constant velocity, it never changes, and the graph would look like this. It would be a constant line, a horizontal line, zero slope. Okay. All right, so this up here would be your 10. And of course it's positive 10 because you're moving to the right. So your line is above the x-axis. Okay? And that's important to note. So a positive velocity, you know, aka this right or east, however you want to look at it. So then your graph is above the x-axis. Like in the positive region of the graph for the y values, right? So there's your VT graph. And if you plotted, you know, at 1 second, or at 2 seconds, or at 3 seconds, you would always have the same velocity. You're moving at a constant speed. Okay, so let's consider a car moving rightward. So again, positive, but with changing velocity. And we'll say that it's speeding up. So if you have a changing velocity, then that must mean that the acceleration is not zero. Okay, so there is some acceleration happening, which is the definition of acceleration. It's a change in velocity. So if your velocity is changing, you are accelerating. You can either speed up or speed down. Okay, and we can draw a ticker tape diagram. Did you guys learn about ticker tapes in Science 10? The ticker tape? So the ticker tape is a way of just marking distances over time. And you can just imagine that these dots are like the car moving, and you're just like taking a picture at that spot. So you can draw like dots. So initially, the dots will be close together, and then they eventually start to get farther apart as you start to accelerate. In this case, speed up. And we're traveling to the right, so the dots are headed to the right. So you can say here, like at time 0, you have position 0. And I can zoom that in a bit. Here would be time 1, position, then we can just make up some numbers. This is 2. At time 2, this is 8. Oh, sorry, let's just use the numbers I'm about to use on the graph. So I apologize. Undo. Let's go with 1, 4, 2, 8, 3, 12. No, this is not right. Sorry. Are you guys using pen? Sorry. Why you guys use pen in physics? Just Giovanni? Sorry. My notes are good. I just got a little ahead of myself. I was looking at the wrong graph. Sorry, you guys. Sorry. Because the last one I had would have been constant, so it didn't make any sense. Okay, so this would indicate a changing velocity. If it was a constant velocity, this time and position would be equidistant. That's what I was writing down by accident. Remember I was going 4, 8, 12? See how they're not equidistant every interval? So that means you're accelerating. And you just imagine a car starting off slowly and then speeding up. Okay? And of course, this will be seconds, and this will be meters. So this would be a ticker tape diagram of an object undergoing acceleration, speeding up to the right. We're good on this page? All right. Okay, so we can draw a graph for this, a VT graph. Now, this VT graph is for the data we just had. And all you need to do is sketch in a line, and I'll sketch it in for you. And then we'll mark some points on it. And you just need to draw like, well, better line than that. Just draw in a line at some angle like this. It doesn't have to be perfect. And we'll just mark in some points. So at 1, the velocity will be 4. That's a position. It's weird, right? The ticker tape is a position versus time diagram. We are drawing a velocity time diagram. And we're accelerating. So the speed will be going up. So as time goes on to the right, your velocity is rising to the right. Velocity is going up. Okay, so and at 2 you can mark 8. And at 3 you can mark 12. Okay, so what do you notice about the velocity change? Is constant. So it's a linear curve. And you have to take these numbers for granted right now. We don't have the skills yet to calculate these velocities from the ticker tape. Okay, we don't have those skills yet. We're just taking these numbers for granted. Okay, so it's linear. Okay, and it's non-constant. And the slope is positive or negative? Positive. And we are accelerating, okay? So the acceleration here is positive. And we'll come to see that these are related. The slope for the VT graph is the acceleration, because it's a change in velocity over a time. And if you look back at these ticker tape diagrams and you try to use like V equals D over T on these, you notice you get issues, right? It doesn't correlate to the graph I've drawn, because you cannot use this for accelerated motion. And you need to accept that right now. We have a whole different branch of formulas that we use for accelerated motion, okay? This D over T is for what? Constant motion only when your DT graph has equidistant points on the ticker tape. That's when you can use D over T, because it doesn't change. But for acceleration, that V is constantly changing, as shown on this graph. Okay? So let's summarize this. And it'll just be two graphs to make a summary. And this is for VT graphs. Okay, so the graph on the left, we have positive or negative V. Which one? Why is it positive V? Above the x-axis. Good. And is it zero slope or positive slope? Zero slope, so we have zero acceleration. Why do we have zero acceleration just in everyday terms? What do you need to have acceleration? Good. Is that speed changing? No. Okay, go into the second graph. Positive or negative velocity? Why is it positive? Above the x-axis. Good. Zero acceleration or some acceleration? Positive acceleration because the slope is positive. Good. So positive acceleration. What's happening to your velocity? This graph, as time goes on to the right, you can follow my pointer. As time goes on to the right, what's happening in the y-axis? You're going up. So as time goes on, your speed is going up. You are speeding up. Okay, you can title this section Positive Velocity versus Negative Velocity. So look at the VT graph, and you just need to check above x-axis, below x-axis. And you have your positive and you have your negative. Pretty straightforward, I think, just reading a graph. And these are the VT graphs. So as I draw this these two graphs, I kind of just want you to follow along. So I'll give you a second to catch up, and then I want you to just follow along as I speak. So I'll give you a second to catch up. Everybody caught up with me? Okay, so this is a VT graph drawn, so it's like symmetric. You have like the positives on top and the negatives on the bottom. So this is V. Just put my pen back on. This is V, and this is T. Okay, so using my pointer, try to imagine what's happening if as time goes on, you're moving up the curve like this. What's happening? Are you speeding up or speeding down? And this is weird. Yeah, good, Kyle. And I'll just put in a number here for you guys. Let's say this is like, -10. Okay, and let's say this is -5 and this is 0. So if you have 0 velocity, are you going anywhere? No. So at -10, are you going faster than at -5? No, it's very specific. Ignore the negative. The negative in physics is just direction. The negative just tells me I'm going south or something, the opposite of my positive direction. So which is faster as a number? This is the magnitude only. 10 or 5, which is faster? 10 is faster. So what's happening as you approach the x-axis, you're slowing. So as the graph approaches the x-axis, you're actually slowing down because in physics, you need to think about the magnitude. 10, 5, 0. Your speed is going down. But now what happens at this spot right here? Kyle, this spot right here at the x-axis. And change of. Good. Guys having a hard time visualizing this? Imagine an object. Man, my pens are no good. Okay. Imagine an object is moving to the left because it has -10 meters per second as a velocity. Let's say I apply some force to the right. Okay, this object's moving to the left, and I apply some force, like say my hand or something, to this object moving to the left. I apply a force. What's going to happen to this object? Is it going to speed up or speed down? Because the force is in the opposite direction as the motion. So you actually will slow down. And now if I continue to hold this force, eventually I'll slow down to a stop, and then I'll eventually start going in the same direction as the force. And that's what's happening here. And if you keep applying the force, and as you continue to get farther away from the x-axis, you will actually speed up. Just think about the magnitudes. Question. Constantly speeding up. What do you mean? Yeah, there would be the next graph will be the other part of it. Yeah. Yeah, that would be negative acceleration. Yeah. So the slope of this line is positive, so it has positive acceleration. Down here you can put v less than 0. Over here you can put v greater than 0. Again, above the x-axis, below the x-axis. The VT graphs are hard at first because you're not used to them. You're only used to these DT graphs. So again, let's draw another VT graph beside it. So this is V versus T. And we can draw now the exact same thing, just sloping down to the right. Sort of like that. So again, what's happening as I approach the x-axis? I'm going from a high magnitude in velocity to almost to the 0, right? So look at the magnitudes. Say this is plus 10, plus 5, 0, minus 5, minus 10. So as I approach the x-axis, my velocity is actually going, and just think of the number, the magnitude only. The velocity is going down. So for that arrow, what do I write? Slowing or speeding up? Slowing. I'm slowing as I approach the x-axis. Now what happens at this, like, what do you want to call it? It's like a threshold point almost. At the 0, there's some switch happens. Change in direction. So now instead of going in the positive direction, whoops, that should say direction. Instead of being in the positive direction, over here where I have positive velocity, I'm now have in the negative direction, I got negative velocity. I'm below the x-axis. And as I continue to get farther away from this x-axis, what would you write there? Speeding up, because the magnitudes of the velocity, the numbers, are getting larger. 5, 10, 50. You're getting faster just in the other way, in the other direction. So this is a huge understanding in physics, is that the positives and negatives just indicate direction. You just think of the numbers as numbers themselves. Like a velocity of 5 meters per second and a velocity of negative 5 meters per second have the same speed, just in the opposite direction. Okay? 5 and negative 5 have the same magnitude, just different direction. Do you want to summarize that in a sentence? Okay. So let's just imagine you're going 3 meters per second to the right, and then now you're going 9 meters per second to the right. That's what the positives indicate. What happened? Speed up or speed down? What happened? Speed up. What about this one? You're going negative 3 meters per second, and then all of a sudden now you're going negative 9 meters per second. What happened there? Did you speed up again? Yeah, because 3 became 9. Speed up. Okay? So the magnitude, and that's key here, the magnitude of the velocity vector is increasing, i.e. the speed, brackets, not the direction. Okay, so this is kind of hard at first. understanding that a vector has two components to it, the magnitude and the direction. All right, so therefore, if line on VT graph moving away from x-axis, you are speeding up. Sorry for the tight squeeze. Conversely, I'll put V down if approaching x-axis. I fit it. What do you guys think? Doing okay? Still need it? Okay, just a quick ticker tape summary. If you're to plot the time versus the position of a ticker tape diagram, if they are equidistant, time position of ticker tape, and we're traveling, the motion is to the right. If it's equidistant spacing, is it uniform or non-uniform motion? So equal space between points, therefore uniform motion. Okay, if it's uniform motion, you have constant velocity. Therefore, acceleration is 0. So what would your VT graph look like? Your DT graph, what does your DT graph look like? DT is linear, like this. What does your VT graph look like? Yeah. Which way a line? Parallel to the x-axis, good. So you would do the slope calculation. Do a slope calculation on dt, and you would arrive at the velocity. And then what would the acceleration time graph of this look like? And I apologize for the squiggly lines. What would the acceleration time graph look like? What does a equals 0 look like on a graph? Right like this? Okay, 0 everywhere. Okay, so this was the uniform motion summary. Now let's do a non-uniform motion summary. Okay, so now on this next page, we're going to draw a ticker tape diagram where the dots start off close and then get farther out. Okay, this is for non-uniform motion. So again, time versus position for like 0 seconds, 1 second, 2 seconds. It starts off close and then they start to get farther apart. So say it's 0, 1, 2, 3, 4. The position would be 0, 5, 20, 45, 80. So these ticker tape diagrams indicate to you whether it's uniform or non-uniform. So you can see that the spacing is not equidistant. So this is non-uniform motion. And non-uniform motion has a dt graph that's not constant and follows a quadratic shape. So it's the parabola. Do you guys know what the parabola is? It's the U-shaped curves. A U-shaped curve like this, you might have seen them in your math classes. Okay, so it would just, about you take half the graph. Okay. So for these, you cannot use this. Okay, so that's a big no-no. That formula is for uniform only. Because there's some acceleration going on, we have these 4 kinematics equations that I'll show you this week. Okay. And now the velocity time graph for this would do this. Here's the velocity time graph. Okay, and if we did the slope on the VT graph, we could calculate the acceleration. And in physics in high school, this will always be constant. Okay, so you find the slope of the VT graph and it's constant, and you'll be able to find the graph of the AT, acceleration versus time. And I'll show you in the kinematics equations, you could actually take this position time data and go straight into the VT, but right now we just don't have the skills for that. Are we good on this slide? Okay. Should we stop there? I can sense the restlessness. Okay, I need to show you what to try for homework. It won't be a lot, you guys, it won't be a lot.